Hello. Okay, this is not very loud. Okay, but okay, this should be a little better. Okay, let's get started and let's talk about the last section before midterm. This is section 3.6, and today we are going to talk about row space, column space, and also two more concepts now in the title, rank and nullity. So I think this is the first more advanced concept about matrices. Okay, so we are going to use all the analysis that we learned from vector space so far, and go back to matrices and analyze the structure of matrices. Okay? And so first we can define two vector spaces associated with any matrix. So we have any matrix A, that's an n by n matrix, and we can think their rows as vectors, and their columns as vectors, and so we have those row vectors and the column vectors. So this is we actually already defined in chapter 1, so here's the review from chapter 1. So we say whenever we have a matrix, we can write it as a list of columns, and we have its column vectors as this a1, a2 to an, and we have that we can also think about the row vectors. So we have also this a1, a2 to an, and with this vector sign on sorry, a1, a2 to an, okay, and with this vector sign on top. Okay. And now we know about vector spaces. We haven't talked about space, but but now we know a little more about vector space. So we think the column vectors are in Rn, so they are just an m-dimensional vector because their length is m. And row vectors are in, so technically it's basically in Rn, but technically it's we write the row vector and the column vector a little different. So we think the row vector is in this weird 1 by n space. So it's in it's actually in the linear space of matrices with height 1. Okay. So this is basically so if you know a bit more about linear algebra, so more advanced linear algebra, people will say this is in the dual space of Rn, but okay, so those will be dual to Rn, but here we are being a bit easy, a bit lazy, so we just say this is in a space of matrices with height 1 and length n. Okay, okay, and anyway, so those are row vector and the column vector. Intuitively, they are just those vectors that has height n, or those vector with length m. Yep. And here are definition. And so we have those row vector and the column vector. Then we can define spaces. Okay. And so row vector will be so we can think about a space spanned by those row vector, and that will be the row space. Okay, so like this here, it should really highlight the span. Okay, so we have all those vectors. We can think about a whole bunch of vectors. You will define a space. That's a space spanned by them. Okay, spanned by the row vector, and so this row space will be a subspace of Rn n times 1. Sorry, R1 times n. And similarly for the columns, we can define column space. It's just a space that's spanned by the column vectors, and there will be a subspace of Rn. And here the notation is a bit important because we are going to use the notation a lot in this section. So the row space of the matrix A, we just write it as Ra, so R for row. And the column space for the matrix A is written as a C of A, so C for column. Okay, so this should be definition and pretty straightforward. And here we have an example. So A is this 1 0 0 0 1 0 matrix. So we have its rows being this 1 0 0 1 0 0. And the row space is arbitrary linear combination between the row vectors. Oh, sorry, row is 1 0 0 and 0 1 0. And so row space is arbitrary linear combination between 1 0 0 and 0 1 0. And so it has this form, and you see it's a two-dimensional subspace because it's a linear combination of two independent vectors. And the column space is the linear combination of 1, 0, 0, 1, and 0, 0. And it's this arbitrary alpha beta vector, and it's everything in R2. Okay. Oh, this is the row space and the column space. Okay. And from here, then we first go to a very important theorem. So we'll talk. So let's first talk about the thing about row space. Row space is very nice because row space is equivalent if you do some elementary operation on your matrices. Okay, so if two matrices are row equivalent, then they have the same row space. Okay, so this theorem will be the basis of a lot of our analysis. And the proof is quite simple. So let's say B is row equivalent to A, and so we can go from A to B by doing a whole bunch of row operation. But if you think about what are row operation you swap two row, or you multiply a row, or you add a row to another row, and all those are linear operations. So when you do row operation from A to B, you are just doing linear operations. You are just doing linear operation on rows of A, and so rows of B will be just a linear combination of rows of A. Okay. And because the rows of B are linear combination of rows of A, so the span of rows of B is a subspace of spans of A. Okay. Because any linear combination from rows of B you can also get from linear combination of rows of A. Okay. So we know row space of B is a subspace of A. And because row equivalence is a symmetric relation, so if you can go from A to B, you can also go from B to A. And so you know the row space of A is also the subspace of row space of B. And yeah, so they are contained to each other, so these two spaces are equal. Okay. And yeah, so this is a very important result. It's nice to remember its derivation, and also very important to remember the result. Okay. Any questions so far? Did you spend a few seconds to memorize this result, because we are going to use this quite a bit today. Okay. So if two matrices are row equivalent, then two matrices are row equivalent, then they have the same row space. So if you do elementary operation from A to B, then A, B have same row space. And I guess you can probably guess here, the thing that we will use most is so when we do row operation, we always like to go to reduce row echelon form or row echelon forms. Okay, so in particular, A and its reduce I guess row echelon form. That's right, REF. Okay, yeah, it's the same. Okay, it's reduced row echelon form will have the same row space, because you can go from A to U, and from U you can do a lot of analysis on the row space of A. Okay, and that's kind of what we will do now next. Okay, so let's define another concept with related to row space. That's the rank of a matrix. Okay, and the rank of a matrix is just defined by the dimension of a row space. So I think this is okay, so now we are focused on row space, and we have one thing about row space, and another thing is row space is a vector space, and we can find a dimension. I guess technically we need to prove, if you want to be very careful, we need to prove that the row space actually have a dimension. But it's pretty obvious. I guess we're going to have a constructive proof now. Okay. And anyway, so the dimension of the row space will be the rank. Okay. And here we just give you, okay, so here is just the definition, and then down here we told you how to find the rank of a matrix. Okay, and it's exactly that you want to do Gaussian elimination to make your matrix into this row echelon form or reduced row echelon form. Okay. So if you want to determine the rank, then you just make your matrix into the row echelon form. Then the number of non-zero row will be a basis for your row space, and so the number of non-zero row is just the rank of your matrix. Okay. So number of those will be the rank of your matrix. And if you want to prove that is correct, then you want to prove that the non-zero rows are actually a basis for your row space. Yeah, and remember, basis you need to prove two things. You need to prove that to be a basis, you need to prove that those vectors has span your space and are linearly independent. Okay, and from theorem 3.6.1, okay, so we use this reference from theorem 3.6.1 because you go from A to your row echelon form. From A to U, you have you're doing row operation. So from this theorem, we know that the span of the rows are the same. So those rows span the same space we satisfy. And so you want to prove this is a basis, then you need to prove that those vectors are actually linearly independent. Okay. And yeah, and well, to show that this is true, you just make it into the reduced row echelon form, and it's very easy to see that the reduced row echelon form, in reduced row echelon form, each non-zero row are linearly independent. Okay. And I guess let's see some example here. So we have matrix A here, and we do our Gaussian elimination. We get this U, this reduced row echelon form, and we kind of see here. Sorry, this is row echelon form here. This is not reduced because you have -2 here. This is row echelon form, and we see row echelon form has two non-zero rows. So 1 and 2. I guess let's use this. So here 1 and 2. So one row and another row here. So we have 2 rows here, and we know rank of A equal to 2. Okay. So rank of A equal to 2 here, and you want to show these two rows are linearly independent. Well, it's kind of obviously they are linearly independent because they have 1 here and a 0 here, so you cannot make a linear combination of them. I guess if you want to, if you go to reduced row echelon form, it will be even more obvious because you have 1 here, 0 here, and 1 here, 0 here, and you can quickly convince yourself that you cannot make a non-trivial linear combination of them to make it a 0 vector, 0 row. Okay, and so that's rank. Yeah. So we have a bit of hand wavy about this part, but hopefully you can convince yourself very quick. You can write down rigorous technical proof, but it will be a bit boring. Okay, so this is rank. And guys, a bit of a spoiler for the later part of this section is that we are going to, so you see this is a bit asymmetric between row and column. So rank of A is a dimensional row space. But actually rank is a symmetric definition, meaning that the rank of A will also equal to the dimension of column space of A. And this is a theorem that will prove later part of this section. Okay. Any question about rank? Okay, this is our definition of rank is equal to dimension of the row space. Okay, if no question, then let's switch a little bit. Now let's talk about column space. Okay, and to talk about column space, so we also go back to chapter 1 a little bit and remember this slide. Okay, so we already talked a little bit about column space. We'll talk about linear combination of columns. That is when you write down this equation. So in chapter 1, we said that when we have this equation AX, this actually means that we are taking a linear combination between columns of A. Okay. So we can think about AX being these columns of A, is A1, A2 to AN, and linear combined with coefficient being those numbers inside X. So it's X1 times A1, X2 times A2, and Xn times AN. This is a very important concept, and we are going to see, and we are now going to see why this is very important, because this can be interpreted as a linear combination on column space. Okay, and so we have Ax, and what we like to write this equation is we always like Ax equal to B. Okay? So now we can think about Ax equal to b as the equation that says that we have a linear combination between columns of A and U equal to this B vector. Okay? And now just from this interpretation, we immediately see that Ax equal to b is consistent if only if b is inside column space. So this is immediate. So b is inside column space, then you can find this linear combination. And b is not inside column space, then you cannot find this linear combination. Okay, so I guess the proof of this statement is here. And this statement is actually our second theorem. Okay. So this is a very important theorem about matrix. So this linear system Ax equal to b is consistent if only if b is inside column space of A. Okay, any question? So this is yeah, and we are going to use this to derive several similar things about this linear system. Okay. So we start with this thing. So we are going to say a whole bunch of things about linear system by saying things on its column space. Okay. So first is Ax equal to b is consistent if only if b is inside column space. So b can be written as a linear combination of columns of A. Okay. And yeah, so first we have this, then we quickly have corollary. Okay. So we have a special case. So we always like the special system is homogeneous system where b equal to 0. Okay. And we think about this equation Ax equal to b of this Ax equal to 0. Then we go back to this linear combination interpretation. Then we have this equation become this linear combination of columns of A equal to 0. Okay. But this equation we see a lot in this chapter. This is the equation for determining whether things are linear independent or not. Okay. So we know this thing has a non-trivial solution if only if those vectors are linearly dependent. This is just a definition of a linear dependence. So this this homogeneous equation equal to 0 has a non-trivial solution. We know this always have the trivial solution of x equal to 0. Okay. And it only has a trivial solution if only if those columns, those vectors are linearly independent. Okay. And so we just reinterpreted this equation. We see that x equal to 0 only have the trivial solution if only if column vectors are linearly independent. Okay. And yeah, so this is very important. So I guess I should give it a red block here. Okay. So this thing will be the basis of basic order analysis in this middle section. So yeah, so very important thing. So they just stare this for 10 seconds and remember this. Okay. A is equal to 0 has a unique solution if only if columns of A are linearly independent. And I guess so while you are memorizing this, I guess one thing to say here is it's a bit confusing because we are going to say a lot of similar statement here. But one thing nice here is that A don't need to be a square matrix. A can be anything. A can be not square. Let me say maybe here. A can be not square. Okay. So this statement works for any A. Okay. So in particular, A can be some m by n matrix where m not equal to n. Okay. And to compare this, let's see some similar statement that we already proved. Okay. So here we have we already run this similar reasoning on theorem 3.3.1. Okay. And but this was on square matrix. Okay. So here's a reminder. So theorem 3.3.1, we say that we have n vector in Rn. They are linear independent if only if x1 to xn are non-singular. And then we also use this theorem 1.5.2 and chapter 2. We have that for square matrix, A is non-singular if only if determinant not equal to 0 and A is equal to 0 only have the trivial solution. Okay, so if you if you string together theorem 3.3.1 and theorem 1.5.2, we have that the same statement, but only for square matrix. We have that x1 to xn are in Li. If only if A is equal to 0, only have the trivial solution. Okay, but now we actually extend the theorem 1.5.2. We see that A is equal to 0, only have the trivial solution, and if only if columns of A are linear independent. Okay, and I guess we can actually extend this because when we were in chapter 1, we were only in chapter 1 we only have we don't have the idea of linear independence, so we can only say things about whether your matrix is non-singular. We only know whether the matrix is invertible. Okay, and being non-singular is a concept only for square matrix. Okay, but now we can cut the middle part, so we can prove this non-trivial solution, only trivial solution at AOI. So this part and this part, now we can connect those two parts without the middle part, where it must be a square matrix. Okay, so yeah, these are the corollary. Any question? Okay, and if not, then let's go to next theorem. So next theorem try to say a little more than the previous theorem, but yeah, it's nice to know this theorem, and it's quite a mouthful theorem. And so the theorem actually has two statements, and both of them true. And so first it says that, so we have this A is equal to B, and I guess this first statement looks very similar to the previous statement. So it's A is equal to B is consistent for every B in Rn if only if columns of A, column vectors of A spans Rn. Okay. And so you look at this and this, they are really similar, and I guess so we kind of do the small gain on finding a difference between the 3.6.2 and the difference between the first method of 3.6.3, and I guess it's a bit fun. So anyone want to answer what's the difference between this statement and this statement? They look very similar. Okay. And I guess this is something we forgot to talk about in logic, and it's actually quite important when you write statement. Okay, and I guess yeah. So the difference is very small, and the difference is between on the quantifier of B. Okay, and yeah. So I guess we actually didn't. So here we should say this is for all B. Okay, so this, we choose B first, and then we have this statement. Okay, so we set any vector B here, and then we have this statement that linear system A is equal to B consistent if only if B is inside column space. Okay, and here we also have for B, but it's in different order. Okay, and it's a bit annoying because it's hard to express this difference in quantifier. Okay, so when you write in English, it's hard to express this ordering of order of your quantifier. But this is actually a different statement than 3.6.2 because it says that. So now we kind of look at A first. So we don't choose B, so we say that if a column of A I guess it's also sorry, I guess it's different, but oh yeah, so we say column space of A. I guess here you see the only if part is also the second part is also different. So we say column space of A spans Rn, but the first statement now looks a little different. So first statement is that So we have X equal B is constant, then we have this for every B in Rn is after this statement. Okay, so how do I express this? Okay, and so so what I want to say is we have that this is a bit different. So we have the second statement happen, then the first statement will happen for every B. Okay. Okay, so the difference here is the second statement. I guess it's easier way to look at this is now you look at the second statement here. This statement didn't say anything about B. The statement doesn't depend on B. Okay, so here this for all B is inside the statement of A. Okay, so here is for all B is the same thing. Then, okay, so the second thing happened, then the first thing should happen for all B. Yeah. So here is different thing about a small issue about theorem. So be careful when you write about quantifier. So whether your for B is outside your statement or inside your, so for B is inside your if only if or outside of your if only if is a slightly different statement. Okay. Okay. And yeah, so this happened then. So if this happened, then this thing should happen for all B. And in particular, so the different part is that so if you have a negation of this statement, that means that okay. So so if you have this thing is not always true, then the negation for both is that is that you will have exist B. I guess that's not right too many notation here. So if you have a negation of this statement, then we will have exist B and negation of this statement. Okay, so negation of for all is exist not. Okay, so this is something that we are going to see in the next statement. Okay, so you have a negation of this statement, then actually the negation is not for all B, this is not true. You just have need to have one B and this is not true, then it's negation. But because we have actually a strong segment, so stronger statement in 3.6.2, we have this pointwise statement. So we actually know that you have this negated, then for all B, this is also negated. Okay. And but then we have also the second statement. Okay, so the second statement is that A equal to B is at most 1. So at most 1 means you have 1 or no solution for all B. And if only if the column vectors are linearly independent. Okay, and so this is similar to this corollary 3.6.2. Okay, so this is this statement going to the version of B not equal to 0. So this is not 0 here. So we know when it is 0 here, then yeah, we have that. You always have a trivial solution, and whether you only have a trivial solution, determine whether A columns of A are linearly independent. And now have X equal to B, and we see that has at most one solution then for every B, and it will be if only if column vectors of A are linearly independent. Okay. And let's see some proof of this theorem, and as they say, when we want to prove the first theorem, then yes, we can actually prove this pointwise. So for every B, it's already true for 3.6.2. So it's pretty straightforward. So if you span everything, then everything inside column space, and yeah, B will then is consistent, etc. And then the second statement, as we say, the only if direction. So if you don't have everything linearly independent, okay. So if A is not LI, then then we only need to find one B that this doesn't satisfy. So we don't need to prove that every B that this doesn't satisfy. So remember the solutions there are 3 possibilities. So there are infinite number of solutions, 1 solution, and 0 solution. And so we want to prove that this statement is not satisfied. We need to find a B that has infinitely many solutions, that has more than 1 solution. And that B will go back to this previous statement, and that B will be 0. Okay, so we only need to know that A is equal to 0 has many solutions. Okay, and this goes from our previous corollary. So we already proved that previous corollary. This is 3.6.2.5 If it's not LI, Ax equals 0 will have many solutions. So only if the direction is satisfied. If this statement is not true, then this statement is not true. Okay. And in particular, so this here is an example of this part. So even if your A, so even if the columns of A are not LI, there can be still some B where you have at most one solution. That means there can be still some B that has no solution. But only need to find one B that has many solutions, and that B is 0. Okay. So yeah, so we talk a lot about quantifiers. Okay. So it's just so we spend a lot of time talking about quantifiers. It's not really related to linear algebra. It's just let you know how to write the theorem statement more clearly. And now talk about the actual linear algebra part of this theorem. Okay, so if those are linear independent, then we want to show that for every A is equal to B, we have at most one solution. Okay, now we need to do some linear algebra. So once again, we start with our 3.6.2.5. So if your A is linear independent, then A is equal to 0, only have one solution. Okay, so it has a unique solution. Okay, and now we kind of go to once again we go to proof by contradiction. So if there is so we kind of go to this part. So we say if there is some B that this is not true. If there is some B that has two non-trivial solutions. Okay, so if there is some B and two non-trivial solutions, and two different solutions, x1 and x2, so they can be trivial or not, we don't care. So ax1 equal to B and also ax2 equal to B. Then we can do we can subtract this ax1 equal to B from ax2 equal to B. Then we have x1 minus x2 equal to 0. But we know x1 don't equal to x2. Then okay, so this is an important equation we derived. So x1 minus x2 not equal to 0, and but a times this difference equal to 0. But then we contradict this a is equal to 0, only have a trivial solution part. Yeah. And so yeah, so we know this cannot happen. So for every B, A is equal to B can only have one solution, one or no solution. Okay, so yeah, so the logic is quite complicated, but the result is quite simple. So this is if columns of A are linear independent, then A is equal to B has at most one solution for every B. Okay. So I guess this is a good exercise on your logic and quantifiers. Okay. Yeah, and I guess that's right here. So here is the logic structure is like so the for OB is outside of your if only. So for OB, and you have something if only if something. Okay. While here you have something if only if something, and this thing is for B. Okay, and those are slightly different statements. Okay, yeah, and here is yeah. So here we'll have for B and some statement that has something to do with B, and statement something to do with B. Okay. So this is theorem, and I think, yeah, and we can compare this a little bit to our corollary. Yeah, so yeah, I guess it's similar. So let's skip this part, and also we have a bit of a note on this thing, and we know that columns of A form a basis of Rm. Rm, then n must equal to m. Okay. So this is kind of from the definition of dimension, because we know if something is a basis for Rm, and we know Rm it has a dimension m, so A must have n vectors. Okay, so A must have n vectors. So but the number of vectors in A equal to n, so n must equal to m. And you can also see this other way. So we know the columns of A must span Rn. Then n must be equal to n, and linear independent, then n must be smaller than or equal to n. Okay, and then I guess see the last theorem about, I think this is the last theorem about column space. So that's this corollary. So we back to n by n matrix, and we say this is a non-singular if only if columns of A form a basis of Rn. Okay. And this is really fast, so we can just go from our previous theorem 3.3.1. So those we know those vectors are linear independent if only if so vectors are linear independent if only if your matrix is non-singular. Okay. I guess this goes the other way. So non-singular if only if the column vectors are linear independent, and we know there are n vectors, and n vectors if n vectors in Rn are linear independent, then for a basis. Okay. Because the number of vectors is already correct. The number of vectors already equal to dimension, and then they are linear independent. So so small review. Remember we said basis we only need to satisfy 3 over 2. So for basis we only need to satisfy 3 over 2. So number equal to dimension and span and Li. Okay, so here we satisfy Li and the number equal to dimension, so we know it's a basis. Okay, and yeah. Okay, so I think this is the end of what we talk about column vector. And any questions so far? If not, okay, then we are pretty on schedule. Then now let's talk about the last concept of this chapter. This section is nullity. Okay, so nullity is the dimension of another space, and the space we talk about is null space, and yeah. So the dimension of the null space is called the nullity of your matrix. Okay, and so we write down. Yes, it is a dimension of a null space of A. So n of A is a null space, and here is a reminder: what the null space of A is the solution set of AX equal to 0. And I guess this 0 should be 0 vector. So let's write a bit of vector sign here. Okay, to remind myself. Okay, so remember, null space is the space of a solution of AX equals 0, and it's a vector of length n. Okay, so remember A is n by n, so the length of this x will be same as this width of A. Okay, so n by n, and A is like this. Okay, and yeah, so this is the definition of nullity. Okay. And what's nice about nullity is now we can have a whole bunch of structure theorems. So we have some theorems that are less obvious than the previous theorems. Okay, so first we have this rank nullity theorem. Says that you have this n by n matrix, then rank of A equal to plus the nullity of A equal to your n, so the length of your row. Okay, and actually later on we have we'll have actually even stronger statement of this theorem. So later on we'll see this Rn. So this space that has a dimension equal to the length of your rows of A, or equal to the row space and plus your null space. And this O plus will be something that we'll talk about later. Okay, so we can talk about addition of vector space, addition of vector space in some formal sense later. But yeah, this is just a bit of spoiler of the later part. But for now, we know that this n equal to this n equal to rank plus nullity. Okay, and this is a very important theorem, and it's not very obvious to see. hopefully it will become more intuitive after we talk about it. Okay. And the proof of theorem is we do our favorite thing is we do our Gaussian elimination, and we have a different order is the reduced row echelon form. Okay. So once again we say we can do Gaussian elimination on A and make it into the reduced row echelon form. So U is the RREF of A. Okay, and now remember our theorem 3.6.1. So I guess let's try to jump back. Okay, remember we said this is very important because we are going to keep using it. So our first theorem on row space, we say we have two row equivalent matrices. They have the same row space. Okay? And in particular, if A is row equivalent to its REF, and A and its REF has the same row space. Okay, and let's jump back here. Okay, and so U has the same row space of A. And because the rank of a matrix is the dimension of its row space, and so we know the rank of A is the number of non-zero in U, row in U, and I guess this is also one thing we already know. Okay, so here when we talk about dimension, we say we can calculate the rank of A by just look at its number of non-zero in its REF or REF. Okay, so it's this thing, and but also there is something extra nice about this thing is U also has the same null space as A. Okay, and so we actually have two statements here. So U has the same row space as A, this we already proved, and U has the same null space as A. And this is not too hard to prove because so here we prove one direction. So say some X is a solution is in some null space of A. So that means A is equal to 0. And then you remember U can be got from A by doing whole bunch of row operation. And the row operation is you just multiply a whole bunch of elementary matrix in front of your A, and so we know all those E times multiply on A times AX equal to 0. So we can have those multiplication of those elementary matrix in front of AX, and this should equal to 0 just by because the matrix multiplication rule. You have a 0 vector multiplying on those elementary matrix is still equal to 0 matrix. Okay. And and those elementary matrix on A. So now we have the associative rule of matrix multiplication. So all those matrix on A equal to U, then we have a UX equal to 0. Okay, and so if something is inside null space of A, is inside null space of X, and you can do other way around. You have something that has a UX equal to 0, then you multiply the reverse of those elementary matrix, and you will get to AX equal to 0. Okay. So this is our quick proof of null space of A equal to a null space of U. Okay, and because the null space of A equal to a null space of A, U, and so null space of so the nullity of A will actually also equal to nullity of U. And nullity of U you can easily see from its REF form that will equal to the number of free variable in U. Okay. And also the rank of A being the number of non-zero is equal to the number of lead variable. And we know the number of lead variable plus the number of free variable equal to this length of your row. Okay. So here we have a bit of an example. So number of lead variable is like 3 here, and the number of free variable is all other empty space here. Or let's see an example with more clear write-up. So here with A here and U here, and number of lead variable is 2 here. You have these two lead variable 1, 2. Okay. Lead variable is this one and this one here, and the number of free variable is this column and this column. So we see that from this U number, the nullity is 2 and the rank is 2. And because A has the same null space and the row space as U, so A also have a rank 2 and the nullity 2. Okay, and yeah, so we finish the rank and nullity, but see more bit more detail about this example. So we know the rank and nullity, and also from this REF, we can also just find the basis for our row space and for our null space. Okay, so here we see that the basis for the row space is just this vector and this vector. Okay. We know these two vectors should span our they are linearly dependent, and they span our row space, so they are basis for our row space. Okay, so this vector, and this vector are the basis for our row space. And then for the null space, we want to look at ux equal to 0. So this thing times x equal to times our 4-dimensional vector x equal to 0, and then you become this equation. So you have x plus 2x2, x1 plus 2x2 plus 3x4 equal to 0 from this equation, and x3 plus 2x4 equal to 0 from multiplying this with your x vector. Okay, and yeah, so lead variable is this x1, x3, and the free variable is this x2 and x4. Okay, and so the dimensional nullity will equal to 2 because you want you can have choose your free variable freely to, and this two free variable will give you 2 dimension of your null space as in this example. Okay, so you can pick your x2 equal to alpha and x4 equal to beta, and then everything in your null space can be written as something like expressed as alpha and beta. So x2 equal to alpha and x3 4 equal to beta, and you can solve x1 and x3 in terms of alpha and beta. So from this equation you have x3 equal to minus 2 beta, and then from here you have x1 equal to minus 2 alpha minus 3 beta. Okay, and yeah, so you have your whole vector as this, and then to our linear combination part, we can separate this into the alpha part plus the beta part. So alpha part is this minus 2 alpha and alpha, and the beta part is this minus 3 beta, minus 2 beta, and beta. Okay, and yeah, so we see this is alpha times another vector plus beta times another vector, and those two vectors will become the basis for our null space. So we see our null space is spanned by those two basis vectors. This is minus 2, 1, 0, 0, and this is minus 3, 0, minus 2, 1. And you can also kind of read from here, so you can think about, well, it's a bit harder, but yeah. Yeah, you can solve this equation, but and then you try harder, you can think about you have free vector here and how those two things relate to your free vector. So you have 1 here, and from here you have a minus 2 here, and from this thing you have a minus 3 here, and then you can have this free vector, and then you have minus 2 here, minus 2 here. You have minus 2 here and nothing here, etc. Okay, but anyway, you can do this calculation slowly, and yeah, so you see that from your REF, you can pretty fastly get your basis for your null space. Okay, and yeah, let's take a 10-minute break, and we will talk more theorem, even more theorem, yeah, next class. Okay, after the break. Okay, I'll take a 10-minute break, and let you look at this theorem. Okay, and let's start. And let's go back to talk about rank. So the first big theorem we prove about rank is this rank nullity theorem. So we prove that rank plus nullity equal to n, equal to the number of column or equal to the width of your matrix. Okay, rank nullity theorem, very nice. And and then now we go back to okay, so this is rank nullity, this is about row space, and now we are going to start combining the column space and the row space. Okay, and yeah, let's keep with this discussion on A and U. So this REF will talk a lot of things about matrix A. Okay, so U is very nice. And now let's think about the column space of U. Okay, so U is very nice because it has the same row space as A, but unfortunately U don't have the same column space as A. Okay, and in general A and U. So this is I should say in general because obviously sometimes you will get lucky. So A and U will have different column space in general. And yeah, so it's unfortunate you cannot just look at the U and get your column space directly, but you can still, you get U, you can still get your column space prefix, although it's not directly the column space of U equal to column space of A. You can still get the column space of A very quickly by looking at the U, as we will see in next theorem. But first we have we need to make this observation that why is U good for knowing the column space of A is because this nullity, this null space statement we had before. So before we said that x equal to 0 if only if ux equal to 0. And now we interpret this equation as some relationship on the column space of A and the column space of U. And we can interpret this as saying that the column vector of A and the column vector of U satisfy the same dependency relation. Means that if you think of this as a linear combination of columns of A, so if you have a certain linear combination of A with your vector x equal to 0, then the same linear combination of columns of U will be also equal to 0. Okay. And let's see those two statements in the previous example we have. So we have that our A is this and U is this. Okay, and we see that the column space of A and the column space of U column space of U are different, very quite trivially, because we will see an example, because the columns of U all has 0 on the less coordinate. Okay, so they are all 0 here. So any linear combination of those columns will have a 0 as the less coordinate. But say the first column of A here is 1, 1, 2, is 1 here, so it cannot be linear combination of the columns of U. Okay, so obviously column space of A and the column space of U are different, because basically every column vector of A is not in the column space of U. Okay, so column space are different. But as we say, x equal to 0 is equivalent to ux equal to 0, and yeah, and so any solution to this will be any solution to this. So say we can have so we write this in a bit of different form. So you see this you think about those column vector a1, a2, a3, a4, and the u1, u2, u3, u4. Then we have a2 equal to 2a1. And U2 will also equal to 2U1. These are pretty easy to see. So you multiply by 2 of this column equal to this column, and then multiply by 2 of this column equal to this column. And you can also check there are more complicated example. So A4 will equal to 3A1 plus 2A3. Oh, sorry, 3A1 plus 2A3, and also U4 equal to 3U1 plus 2U3, etc. Okay, so the dependency relation will be satisfied. Okay, and yeah, and by knowing these dependency relations, dependency relationship same for A and U. Now we can derive the theorem that we have been hinting. Okay. So this is the theorem says that the dimension of a row space equal to the dimension of a column space, and this equal to rank. So the theorem says that rank is a symmetric definition between row space and the column space, because the dimension of a row space equal to the dimension of a column space. Okay, so this is I guess our rank theorem. Okay. And yeah, now let's start proving this theorem. So with dimension of row space equal to the dimension of a column space. So we prove this in 2 steps. For first step, we are going to prove that the dimension of column space is greater or equal to the dimension of row space. And then we are going to prove the reverse direction of the dimension of row space is greater or equal to the dimension of column space. And then from those 2 equations together, we know that these 2 dimensions must be equal. Okay. And to prove this, then we start with our favorite thing. We do our Gaussian elimination, and we get our REF. Okay. So we have some REF that's U equal to the REF of A. Okay. And yeah, so the first derivation of this first thing is more complicated, and we are going to do something very funny, and I guess it's easier to see this in example. So back to our favorite example 3. So we have A and its REF here, and we are going to delete some colors of U and A and get this AL and UL. Okay. So this is an operation that's very hard to describe in words, but easy to see here. So we just take the columns from correspond to the lead variables of U, and then the corresponding columns from A. Okay. So you see that. So the first thing, so we have A and U here, and so the first thing we do is we get this UL. So you just look at the lead variable here. So lead variable is this 1 and 1, and the lead variable has its columns. So maybe we can call it the lead columns. So we take the lead columns together, and we get this UL. Okay, and then now we look at the indices of the lead columns. Okay, so this is the first column and the third column here. So we see we go from U to L. We take the first column and the third column, and then we can take AL from the corresponding columns of A. So the first column of A and the third column of A, we get this AL. Okay, so this is our UL and AL. So yeah, so the most complicated part of this proof is describing this AL and UL. Okay. So we can we have a U, we take A, and we get REFU, and we can take these lead columns to get the UL, and we get the corresponding columns to get the AL. Okay, and yeah. And yeah, so this is the most complicated part of this proof, how you get UL and AL. They kind of go in circle. Okay, everyone okay with how to construct AL and UL? Yeah, and yeah, so if we have this UL and AL done, then now it's just a whole bunch of derivation to get the dimension of a row is less equal to dimension of a column. Okay, so dimension of a row space is equal to, as we know, number of non-zero rows of U. Okay, number of non-zero row, and that will be equal to number of lead variables, so number 1 here. Okay, and the number of lead variable we can count in both row and column. So number of lead variable is also equal to number of columns of UL. Okay, because that's what we do. For every lead variable, we get a column from U. Okay, number of lead variable from UL, and that will also be same as the number of columns of AL. Okay. And yeah, and yeah, so number of column of AL is less than is equal to yeah, number of columns of AL is equal to the dimension of column of dimension of the column space of AL. We really need. Okay. I think the proof can be a bit easier, but okay. So the proof can be a bit easier, but this way to prove things will be something nice that we'll use later. So let's keep this more complicated proof. Okay, so so number of column here is actually equal to the dimension of column space of AL. Okay, so I guess here is the most tricky part of the concept here. Okay, so why is the number of column here equal to the dimension of the column space of this weird vector space? Okay. And so we'll have two vectors, and we want to say those two vectors is span. Those two vectors is sorry. Should I say the space of those two vectors is 2, means that the two vectors are LI. Okay. So we want those two vectors is the basis of the space they span, and we need that. One layer to be a basis, then they need to be LI. Okay. And so why they are LI is because the dependency relationship we talked about. Okay, so and so we want this thing here. Okay, so this question mark here that we didn't give you time to think about, but so we need that the columns of A are LI, and that's because the columns of U are LI. Okay. Sorry, columns of. So we want the columns of AL are LI, and that's because the column of UL are LI, and columns of UL are LI because well, it's quite obvious to see here, because the columns of U will just be standard vectors. Okay? Because U is a REF, and you know for every lead variable you have a 1 and a 0 other word. Okay, so column of U will just be standard vector, the standard vectors, and we know standard vectors are always linear independent to each other. Okay, and so columns of U are Li because they are standard vectors, and that will also mean columns of A are Li because this is where we use this dependency statement. Because A has the same dependency statement with U, and so Ux equal to 0. The columns of UL are Li, so Ux equal to 0 only have the unique solution from our favorite theorem before, right? So our let's see, our favorite corollary, this thing. So we have Ux equal to 0. Only have so U has Li columns. So let's write it here. So think about Ux equal to 0. How many solutions is this thing? Okay, so U has a linear independent columns. So maybe UL. Okay. So we have that UL has a linear independent columns. So UL equal to 0. Only have a trivial solution, and but we know the solution set of AL and UL are the same. So that means AL x equal to 0 also only have the trivial solution. And let me go back to here. That means AL has a linearly independent column vector. Okay, so we go like 4 ways. So UL has a linear independent columns, and go to UL equal to 0, only have a trivial solution. Then from the dependency relation, we know UL equal to 0 has the same solution of AL equal to 0, and from AL equal to 0 only have a trivial solution. We go to A has a linear independent columns. Okay, so yeah, let's go back to where are we about here? 17. No, a bit more. Okay, yeah. So once again, we use our corollary 3.5. Sorry, 3. I guess we call it 3.6.2.5. Okay, and we use dependency, and we use this equivalence between UL x equal to 0 and x equal to 0. And I guess one thing we didn't say is the same dependence was A and U. We have that A is equal to 0 if only if Ux equal to 0. But this is why we take the same corresponding columns from A and the same corresponding of columns of U to get the UL and AL. And so from this dependency relation, we will have that AL equal to 0 if only if UL equal to 0, because we are taking the same corresponding columns. Okay, so yeah, so this is the hardest part of the proof. We have that AL have independent columns. Okay, so we've spent a lot of time to say AL have independent columns. So those two columns will span those two columns will span the column space of AL. Okay, and yeah, then from here, then we can get finally we get our less or equal to direction. We have dimension of column space of AL is less equal to dimension of the column space of A. And this is just because A has more columns than AL. Okay, so A has those columns and the other two columns, and then you add more columns, you will only spend more space because there are more linear combination you can make. Okay, and yeah, so this is the whole proof. I guess yeah, the tricky part here is here, and I guess the smart part is actually here when we take a lead variable. So when we take a lead variable of U is where we switch from counting number of rows to counting number of columns. Okay, so yeah, so we were saying dimension of row of A is a number of non-zero rows, and also equal to this number of lead variable here. And then we start counting columns here. Okay. So yeah, so this is the hard part of a proof. And as we say, the next step is we are going to prove the dimension of row space is greater or equal to the dimension of column space. And this is actually not very easy because we can just do the same thing on the transpose of A. Okay, so we now just think about AT and do the whole same thing. So the row space of A will be the column space of AT, A transpose, and the column space of A transpose. Sorry, and the column space of A will equal to the row space of transpose of A. Okay. Yes, because that's what transpose do. The transpose between row and column. And so we know the column space of AT has a dimension greater or equal to the row space of AT, and that means the row space of A is greater or equal, has a dimension greater or equal to the dimension of the column space of A. Okay, so that's the second part. Okay, and so from those two things, we see that the dimension of row space equal to the dimension of column space, and equal to rank. This is the rank of A. Rank of A equal to those two things. Okay, so finally we finish our most important theorem of the first section of our course. That's rank equal to dimension of row space equal to dimension of column space. Okay, and from this theorem, we not only prove this, also this AL and UL restriction give us some nice algorithm. So this also gives us an algorithm to find the basis of C of A. And so this is kind of why we need to make this, I think, a harder proof. Okay, so from this harder proof, we give a way to find the basis of C of A. Okay. And it's this part. So actually, now we know the dimension of AL equal to also equal to the dimension of A, because this thing equal to this thing. So this is actually an equal sign here. Okay, so dimension of AL equal to dimension of A. So actually those two vectors just span the whole column space of A. Okay. And so here is a way to find the basis of A. So you get the REF, and you look at these those two lead variable, and so then those two corresponding columns will be the basis of your column space of A. Okay. So so this is what the extra thing we get from this hard calculation. We see that you want the basis for your column space, then you just take the vectors inside your AL. So those two will be a basis for your column space. Okay, and so the nice thing about this algorithm is your basis will be a subset of your columns. So you see, you take two columns of A, and this is these two columns span your column space. And also from the other way to prove this theorem, we see a way to get the basis of your column space is you just make a transpose of your A, and you try to find the basis for your row space of your AT. And we know how to find the basis of a row space is you do Gaussian elimination on the transpose of your A. And when you do this, you will find the most standard basis, because say here you see the REF, you will get those lead variable with 1, etc. Yeah. So you will get the most standard basis of your columns if you would do this transpose and the Gaussian elimination. Okay. And I guess here, I guess I should say by finding REF of AT. Okay, I should say REF. Okay, and so those are the two ways to find the basis for your column vector. And also those two things that you do are ways to find a basis for basis for the space spanned by some vectors, because you can just think your vectors are some column vector, and then you can find the basis for them. And then you check whether your number of your vector equal to a number in your basis. Then you can determine whether your vectors are linearly independent. And this is something, a generalization of something we do in theorem 3.3.1. Remember, we said that we want to test whether some vectors are linearly independent. We write down this equation. So we want to check the linear equation xc equal to 0. And then we have this x matrix is just you list every vector here as a column vector, and we want to check whether they are free variable. And we say if they are free variable, then your vectors are linearly dependent. Okay, and yeah, so this is kind of what we do. Kind of what we do before. Okay. And yeah, now we know more general form to do this. We also find a basis for the column vector, etc. Okay. And I guess this thing will be a generalization of what do we do in algorithm 1. So we have the column vectors, and we make it REF. Then we count the number of leaf variables. And we find the basis for those column vectors out of those column vectors. And if the number of leaf variables don't equal to the number of columns, then we know that there are some linear dependent columns from this algorithm 1. Okay. And yeah, so this is our algorithm to find the column space. You make a Gaussian elimination once again. And yeah, so let's see an example. We have a big matrix, and then we make it into actually only REF, because we are a bit lazy, so we only make it into REF. So we see there are 3 leaf variables here, and we know those 3 corresponding columns will be so this column, this column, and this column will be a basis for the column space of A. So this column, this column, this column 1, 2, 5, and this also means the rank of A equal to 3. Okay, and then we also can also do similar things. So in different formats. So we have 4 vectors here, and we'll find the dimension of the space spanned by them. So we list those 4 vectors into a matrix. And once again, we do reduced relational form. We see that they only have 2 leaf variable, and so the rank equal to 2, and the basis is just this first vector, these 2 first vectors. Okay. Yeah. So x1 x2 is the basis of your vector space, and dimension equal to 2. Okay. And finally, we have a checklist. So checklist is everything we talk about today. And we have an extra checklist for the algorithm to calculate the basis for row space, null space, and column space. And basically what you do is you do a lot of Gaussian elimination to find your REF. Or if you are lazy, I think most of the thing you can do by just finding REF. Okay, so you can do a bit of lessing. Okay, and let's skip through the checklist first, because we have a bit extra time, and let's talk a little bit about something extra. So something that we don't cover too much in this course, but nice to know that it exists. That's infinite dimensional vector space. So far we have been talking about finite dimensional vector space, basically Rn. And but mathematically there are also infinite dimensional vector space. So those are vector space where when you try to find a basis, you find the basis have infinite number of elements. And yeah, so I guess let's talk about 2 vector space that will be used in a bunch of different areas. Okay, so first is the vector space of polynomials. Okay, and so we can think about polynomials as a vector space. So we write polynomials of x as this p of x. Okay, so and we still only talk about real vector space here, and so let's think about polynomial with real coefficient here. Okay, and so well we have those set of polynomials, and we can define addition and scalar multiplication on the polynomials. So addition, so you have some polynomial p and a polynomial q. So I have some p of x and a q of x. We can define the addition. So we have this added polynomial px p plus q of x, and it just you do well the polynomial addition. So p of x plus q of x, and so I guess I should write some example here. So maybe p of x is x plus 1, and q of x is x squared plus 1, and then you have px plus q of x is you do polynomial addition, so that's become x squared plus x plus 2, something like this. So this plus this equal to this. Okay, so you can do polynomial addition, and similarly you can have scalar multiplication, and so maybe you have twice times 2x plus 1, then you have 2x plus 2. Okay. And so I guess a thing to emphasize here is that when we think about this vector space of polynomials, we think a polynomial as some I guess a symbolic is a symbolic expression about x. So x is just an algebraic symbol here. So this is an important concept. So you don't ask what is x here. X is a symbol here. So and polynomial is a symbolic expression about x. So polynomial. So this x plus 1 is just x plus 1. Is not you don't ask what is x here. X is just a symbol. So we want so we have a way to add those symbols together. So we have this x plus 1 expression about x plus this x squared plus 1 expression about x here, and then you get this another expression about x here. Okay. So polynomial is an expression about x. Okay, and yeah, I guess here we have a more written example. So we have p of x equal to this 1 plus 2x squared, and the q of x equal to minus x, and plus q of x equal to this thing, and 2px equal to this thing, etc. And you can check the axions, and you see that the axions. I guess the closure is pretty obvious. So whenever you do this addition and multiplication, you still get a polynomial. Okay, we have a polynomial of x. You do those addition and multiplication, you still get a polynomial of x. And you can also check all the axions about those addition and multiplication, and they will be satisfied. And this is really a vector space. And okay, now go to the hard part of vector space. So we can think about what's the zero vector inside this vector space. Okay, so anyone want to answer? What's the zero vector inside this vector space? Okay. And anyway, so you can think about what's the zero vector. There is one polynomial that's zero vector. That's 0 for scalar addition here. Sorry, for vector addition here. And also now you think about what's the basis of this vector space. Now you get infinite. Okay, so yeah. Okay, so you want every polynomial as written as a linear combination of your basis element, and I guess very natural addition. Sorry, natural peak is basis is just all the monomials. So it's 1 and x squared and x3, etc. Okay, so say here you have 1 plus twice times x squared. Okay, and here you have 1 plus minus times x plus twice times x squared, etc. Okay, but you think about what the dimension of this vector space, then you see that the number of elements your basis is infinite, because there you can have infinite number of powers on your x, and any power of x is a polynomial. So yeah, so the number of basis element is infinite, and yeah, this will make a lot of property of the vector space tricky when you because there are some mathematical complication around infinity. Okay, but we don't go into detail. Just saying that the basis has infinite number of elements here, and the basis is technically infinite dimensional. Okay, and then we have another infinite dimensional maker space that people will see a lot is this vector space of functions. Okay, and this is actually something. I guess let's do a bit of advertisement here. So this vector space is something we will see in signal and processing course. Okay, so a lot of signal and processing is talking about this vector space of functions. Okay, so you can think about a function. So if you are given some interval between a and b, and you can think about functions on this defined on this interval with a real value. And once again, you can think about function addition. So you have addition of two functions in this interval a and b. Then is you just define this added function as every point x is just f of x plus g of x. And similarly, you can have scalar multiplication. You have for every point of x, this alpha times f of x is just alpha times f of x. Okay? And so for all x between a and b. Okay? And so you can have, for example, you can have your a and b is between, say, 1 and pi over 2, and you have your p of x is the sine of x, and q of x equal to minus x, and you can have p plus q of x equal to sin x minus x, and this is just some function that we will define between 1 and pi over 2, and 2p of x is 2 sine of x. And once again, you can check the extents of this addition and the scalar multiplication. You see that this is actually a vector space, and then you can see that you can also find the zero vector. It will be some function between this interval, and finally the basis of there are also some kind of concept about basis of this vector space, and now the basis is even more complicated concept on this vector space. Okay? Because you cannot really even find a clear basis for this vector space. Because so in this vector space, the bases are kind of countable infinite, so you can kind of feel that you can count the basis element in this vector space. But in this vector space, the basis kind of feel that it's a continuous thing. So everything is kind of a basis, okay? And yeah, it's real hard to define a basis element here, and yeah. So finding a basis of this vector space is even harder, and people will try to do some kind of thing to define a basis for this vector space, and yeah, that's something people do in signal processing. But there are a lot of complications of trying to define a basis here because this space is really huge. Okay, and yeah. And well, that's something people study more in calculus, but in terms of linear algebra, we just need to know that the space of functions on some interval can be also viewed as a vector space with a very undefined basis and a very undefined dimension. Okay, and yeah, so that's all we want to talk about in this chapter. In this section 3.6, so I guess you can stop early here, and yeah, you can ask any question after the class, and I think on Wednesday we should have a midterm review, and on next Monday we will have our midterm. Okay, yeah, so see you on Wednesday. Yeah, I think homework 6 should be included, and there should be no homework this week. Okay. Yeah. Okay. So yeah, see you next time.